In the course overview, we talked about the state of systems and how one uses physical properties to specify those states. And in particular, we noted that pressure, volume, temperature, number of moles of particles were among the physical properties that we would be most concerned with. Now, I think that pressure and volume are probably pretty easy for us to understand, and we can certainly understand number of moles. But the one quantity here that is a little bit more difficult, a little bit more elusive, is temperature. So I want to spend a few minutes talking a little bit about how we can begin to think about temperature, and we'll be developing our ideas about temperature throughout this particular lesson. Now, before I get started, I'd like to note that there is a very special book that you should take advantage of if you can, and that is a book by John Fenn called Engines, Energy, and Entropy. And some of what I'm going to say here comes from that book, but he does a much better job of describing it. So I'll refer you to that, and if you have a chance to get a copy, it's a wonderful book published about 40 years ago, but very nice explanation of thermodynamics. So when we talk about temperature, we have an idea that it basically helps us to distinguish such things as hot and cold. All right, but the quantitative measurement of these concepts is a little bit more elusive. It's more of a comparative comparison, a comparative thing. We know if something is hotter than another, and we know if something's colder than another. We also have an idea that if we bring two things together and they have a different degree of hotness or coldness, that eventually they will exchange something that will enable them to achieve the same temperature. This is something that we'll come to know as thermal equilibrium. And it's basically the point at which two objects would have the same temperature. And this is something that will play a role, as we'll see at the end of this lesson, in the zeroth law of thermodynamics. All right, but before we get that far, let's talk a little bit about how we might find a way to measure temperature, how we might actually give it some sort of quantitative basis. Well, there are lots of things that have been tried through time, but I'll say that the most successful, or at least the one that seemed to gain a foothold the earliest, was in noticing that there was a certain relationship between gases and temperature. And that is to say, the hotter a temperature got, the more pressure a gas might feel, or its volume might expand. And so the earliest techniques for measuring things like temperature actually had to do with gases, and we can call them gas thermometers. And the whole idea is this: if we hold the volume constant, so we're going to put a fixed box in which a gas is held, and we find a way to measure the pressure of the gas within that box. As we change the temperature, we can observe that the pressure will change. And in particular, the pressure is proportional to the temperature in that box. So if I have two different states of the system in that box at different temperatures, I could easily record that the ratio of the pressures at those two states is equal to the ratio of the temperatures. That's one way that we might quantify this concept of temperature. And this actually leads to, I think, some very fruitful observations through time. Now, how does one fix a temperature, though? One way that we do this is by specifying a particular degree of hotness at which water would freeze or which water would boil. And at these two temperatures, one can hold a boiling mixture of water next to a container containing a gas and then measure the pressure of the gas once that gas has achieved the same temperature as the boiling water. Or we could do the same thing with freezing water and measure the pressure. And so it turns out that this provides us with a way of, if you will, at least quantifying a ratio like this of two temperatures that are related to boiling water and freezing water. And this is our first method for for generating a scale that would help us quantify that amount of temperature. All right, now this can be done with lots of different gases. I mean, you can imagine I have a sample here that's got the water in it, and I'm going to either heat or cool this water down until I'm achieving freezing or boiling, and put this adjacent to my container that contains the gas. And it's this container now that I'm going to measure my pressure at these two different temperatures. Well, it turns out that for a variety of different gases, so we can use many different kinds of gases, methane, argon, carbon dioxide, whatever we want to put in there, it turns out that if we're starting off with a low pressure gas, so we're dealing with a very dilute sample in the gas mixture, it turns out that this ratio that we get of boiling to freezing turns out to be the same. And in fact, this ratio, so I'll put this as T boil over T freeze, is about 1.36609. And in fact, this is, it seems like it's overly precise here, but this actually is precise to about this margin of error. So this is a very firm number for the boiling and freezing temperatures of water. And so then the question comes, how would we talk about temperatures in between those two, or how would we talk about temperatures that are outside those range of temperatures, and do it in a way that is consistent with this temperature? Well, this is leading into subjects that are deeper than I really want to go into, but let's suppose that what we do have at our disposal is that we can set a range of values. We're going to, for example, posit that the freezing temperature is less than the boiling temperature. And what I want to do is I want to set an increment of several different temperatures in between them when I go up this increment of steps, I would eventually go from the temperature that corresponds to freezing to the temperature that corresponds to boiling. Now, we can be arbitrary with this. It could be 2 steps. It could be 10 steps. Well, it turns out that there are a couple of possibilities that have been tried historically. Perhaps the earliest was done by Fahrenheit, which set 180 steps between these two temperature differences. And then later, one by Celsius that used 100 different steps between temperature of freezing and temperature of boiling. All right, so if we have 100 steps, what does that imply then about these temperatures? Well, I'm going to say that, for example, T boil is equal to T freezing plus 100. So what does that give me over here? Well, if I have T freezing plus 100 in the numerator and T freezing in the denominator, that's just 1 plus 100 over T freezing, and that's equal to 1.36609. All right, well, I can solve this equation for T freezing, and I invite you to do this. It's a great exercise. It's not very difficult. And what one would find is that the T freezing in this particular case would be equal to 273.156. All right, well, you probably recognize that number because it's associated with one of the temperature scales that you have been introduced to. All right, so in essence, what this is saying is that because of this ratio and this very common and universal behavior of gases when subjected to these temperatures, we can now define a temperature that we would ascribe to the temperature of freezing. And since we have now arbitrarily set the increment of temperature at 100, that tells us immediately that T boil will be 100 greater than this, or 373.156. All right, so we have these two scales. Now, this, as it turns out, is a scale that is due to William Thomson, who was also known as Lord Kelvin. And the Kelvin scale is one in which these are the temperatures at which water boils and freezes. It also, though, goes down to a temperature of 0, which corresponds to absolute 0. And it is a very special point. We can't go below this temperature no matter what we do. And toward the end of this lesson, we'll find out why that is. Now, Kelvin scale is not the only one. I mentioned Fahrenheit scale up here. If we go into both what Fahrenheit and what Celsius did, they did not set the temperature of freezing at 273. In fact, Celsius set the temperature of freezing at 0, and Fahrenheit set it at 32. So it means that we have 3 different scales here, and what I'm going to do is relate them all together like this. If this is our temperature of freezing, and this is our temperature of boiling, the Fahrenheit scale would set this at 32 and this at 212, 180 degrees higher. So this is degrees Fahrenheit. Degrees Celsius would set this at 0 and this at 100. And Kelvin would set this at 273.15 and this at 373.15. So if we're given these different scales, we actually can derive formulas that relate these temperature scales to one another. So for example, the Celsius scale could be equal to the Fahrenheit scale minus 32 and then times 5/9, which scales us back from 180 degree differences to 100 degree differences. The Kelvin scale is equal to the centigrade scale plus 273, because both of them correspond to a difference of 100 degrees between the freezing and boiling points of water. All right, so we can use these now to derive a set of scales for temperatures that we can interconvert to one another. In this course, we will be using exclusively the Kelvin scale. Now, occasionally I will talk about increments of 1 degree centigrade or 1 degree Celsius. That is the same as an interval of 1 Kelvin, because they both have the same interval here between these two. All right, but we will practically never discuss Fahrenheit. In fact, the most you'll see it is in some practice problems and in some basic skills problems. So please get in the habit of converting all of your temperatures to Kelvin before you work problems.